Who wouldn't love a heat pump? It's a magic box typically that sits outside that heats your building, cools your building, may even provide some domestic hot water in the traditional sense. That is magic. Still, I'm amazed how they extract heat when it's negative 13 degrees outside and how they cool when it's 120 degrees outside. It's an unbelievable piece of technology. I think that people underestimate and underutilize and almost don't believe it. Yeah, it's magic. Yeah, I love them.
Hey everyone. Before we dive into today's episode, I want to take a minute to ask for your help with something really important to Amply's mission. We are hiring a senior iOS engineer, and I suspect the person we're looking for is somewhere in this collective network. Maybe it's you, maybe it's someone you know, maybe it's someone who knows someone you know. Here's what makes this role special. Amply's mission is to help get more heat pumps installed, and more importantly, to make sure those heat pumps are perfectly sized for each home. We're not just building software, we're helping solve one of the biggest residential decarbonization challenges we have. Amply is an awesome place to be an engineer. Why? First off, I'm literally the only non-engineer at the company. It is an engineering-driven culture where everyone gets deep into technical details because that's what it takes to solve these complex problems. Second, we're super early stage, which means any engineer who joins us is not just writing code. They're wearing a product management hat. They're getting to know our customers. They're walking in our customers' shoes and then figuring out how best to solve their problems. There is zero bureaucracy here. We don't have a bunch of leadership and hierarchy and standing meetings. We are extremely flat as an organization. We make decisions fast. That can be super exciting if you thrive in that kind of environment. The other thing that's really exciting right now is that our product is catching on with customers. We're getting fantastic feedback, but what we keep hearing is, we want more, we want this feature, fix this. Our customers are clear about what they need next, and we know exactly what we want to build. So you'd be joining at this perfect inflection point where product market fit is happening, and there's this clear roadmap ahead of super important stuff to build and roll out. We're looking specifically for an iOS engineer with Swift and SwiftUI experience, someone who's built apps from concept to launch, and who loves creating beautiful, intuitive experiences. If you're listening, here's how you can help us. First, the job spec is the very first link in our show notes. Check it out, share it. Second, if you're on LinkedIn, the job spec is my pinned post. It's also Eric's. Feel free to repost it or share it on Instagram, Facebook, whatever, wherever your network hangs out. But here's what I'd really like to ask you, if you're willing. Take 20 seconds right now to rack your brain. Think about your network, not just the obvious connections, but the ones once or twice removed. Your cousin's boyfriend who's an iOS developer, your neighbor's kid who graduated a couple years ago with a CS degree and seems whip smart. I am confident that the right person is in our collective network, and finding great people through referrals is our favorite way to hire. If someone comes to mind, send them the link. If you know someone who might know someone, share it with them too. This role is all about helping heat pump pros do their best work, which means more homes get electrified the right way, more happy homeowners, and honestly, that's how we all win. All right, that's it. Sorry that took so much time, but this is super important to us. Thanks for taking the time to think about it. Now let's get on to today's episode. Hi, and welcome to the Heat Pump Podcast. I'm Ed Smith.
And I'm Eric Fitz. We are co-founders of Amply Energy.
Today, we've got Ross Trethewey. Ross is the founder and principal engineer at TE2 Engineering, and he's also the building engineer for This Old House on PBS. Ross, thanks for joining.
Thanks for having me, guys. Excited to talk to you. I saw you at the symposium. Nice to see you. We'll talk some more about heat pumps and all this good stuff.
Okay, so lots of folks know you, Ross, from you being on the scene, you making presentations and whatnot. I think places like the symposium, social media, This Old House. But for those who don't know you, give us a quick sense of TE2 so they have a sense of like the work that you do. So who are your customers and how do you help them?
So yeah, TE2 Engineering is the company I started back in 2010. So we've been doing it about 15 years now. And our kind of main part of our business is providing consulting engineering services for primarily mechanical systems, but also electrical, plumbing, and fire protection. So we do MEP, FP. And our bread and butter project is a high-end custom residential project. So this would be a single family dwelling that might be the size of a commercial building, so to speak, that has an architect and has a lot of different players the stakes are pretty high. But the reason that we're involved and we like those projects is because we've got the budgets to be able to do some creative stuff, and we can basically try to provide the goals and expectations that the client's looking for. And we get these weird requests sometimes from clients. And so we're able to meet them with what their goals are, what their expectations are, and provide a mechanical plan or electrical plumbing fire protection plan that meets the needs of that building and what they're looking for. And a lot of times it takes us into geothermal, ground source heat pump design. It takes us into air to water heat pump design and solar and net zero buildings. And we get into these kind of creative solutions and strategies. So it's exciting to work on those projects where we're not trying to fight every single dollar and it's super budget conscious, where these projects have a little bit of flexibility in terms of how they're conditioned. And we have the budgets to do those kind of creative systems. So that's where we want to play. That's where the majority of our business is. We also do more just traditional manual J, manual D, manual S designs for more traditional residential projects. And we also do some commercial projects. We do some multifamily development. We're doing an event center right now. So we do commercial buildings as well. But that's generally about 20 to 30% of our overall business.
Very cool. When you say these very large homes, what square footage are we talking about that's typical or where it almost looks like a commercial site?
You want the real answer or do you want... No, it's...
I want both. Give me the real and the lie.
No, so these projects are big. So I would say some of the high-end residential projects start off at maybe 8,000 square foot homes.
Okay, yeah.
And the largest one we've worked on is about 45,000 square feet. Of course, that's over multiple buildings. So it might have a main house, a pool house, a guest house, potentially a cabana, a game room. So some of these are for ultra high net worth individuals that want their compound on Nantucket or whatever. But so we do get pulled into those projects, which are obviously high stakes and very interesting. But yeah, so we run that spectrum from, call it 7,000 all the way up to very tens of thousands of square feet of space.
So this is great. How does Bob Kraft heat and cool his second home? No, I'm just kidding. That's helpful, and would love to get into some of the creative solutions that you have, because I think there's a lot of interesting stuff there. But Eric, I'll give it to you for the next one.
Love to hear more just about you. Tell us about your own personal path. I know you're a recovering mechanical engineer just like me, but how did you get into this and end up where you are today?
Yeah, I think it starts off, I'm a fifth generation plumber. So my great grandfather came over from England to Boston in 1902 and started Trethewey Brothers. That was when plumbing was new. Before that, they threw sanitary waste out into the street. So it was a very different time back then, but I think growing up in the basically fifth generation, all my uncles are plumbers, my dad's a plumber, my grandfather's a plumber. All I knew was plumbing. So guess what? Every summer was all about plumbing. Every discussion around the dinner table was about plumbing. So I probably soldered a pipe at 5 or 6 years old. So I had, I think, a really foundational understanding of plumbing systems from an early age. And so that was a starting point, I think. But from there, basically, I was curious about the systems, less about the installation and more about why. And I think ultimately the curiosity is what kind of drove me to go into the more engineering path. So I was curious, why PVC piping for drainage? Why cast iron? Why? And then it got evolved into heating and cooling systems. And so my bachelor's degree was in mechanical engineering. My master's degree was in sustainable energy, was in solar. And so I didn't have a crystal ball, but I thought, hey, the future will probably involve some sort of renewable energy. I was full deep dive into solar, geothermal, ground source heat pump design, et cetera, wind, big into that, and trying to figure out how these buildings in the future would be electrified, conditioned, and powered. I also grew up on a sailboat every summer. And so it was the closest that my dad would say that we could go to going to the moon, where we would do a sailboat race, let's say from Newport, Rhode Island to Bermuda. And so my dad says we were hijacked, my brother and I. The kids were hijacked. We stayed out of trouble, but we learned a lot of stuff about how buildings survive and how to live within your means in terms of what you have. And so we had a limited amount of water supply. You have a limited amount of electricity. We had solar panels. You have batteries. And so I think, and also being able to be self-sufficient, you learn how to service those things and troubleshoot those things on the fly because you're out in the middle of the Atlantic Ocean. You don't have anybody to call and figure out. So I think some of the experience early on set me up for that kind of engineering pathway. And then basically from there, worked for a HVAC contracting business, an HVAC engineering business, a manufacturing business, went to Europe and studied with them in their R&D plant in Germany, France, and Spain. And so was able to get an experience from the European perspective. And at the time, they were paying like 40 cents a kilowatt hour. So they were doing stuff that was obviously far superior to what we were doing here in the States, where energy was cheap. And so I got a really good perspective from that. And then obviously started the business in 2010 for my consulting business. And then in 2011 was the first time I was on This Old House. So that was the start of the TV show. And it was about the first segment I did was solar. So it was a pilot, first segment on solar, and they didn't call for 5 years. So I was like, oh man, I must have done a horrible job. The phone did not ring after that. But 2016 became a full-time cast member.
Got it. And how much of your time, I'm just curious, split between being part of the cast and doing all the production versus your role at TE2? What does that split look like?
Yeah, it kind of ebbs and flows. When we're doing heavy shoot days, a lot of production meetings, a lot of shoots. Obviously, that's going to be heavily going to be focused on This House and Ask This House, but the majority of the time is spent at TE2 Engineering. So I'd say it probably is maybe 80-20, something like that in terms of my time. 80% with TE2, obviously 20% with the TV side. So it's a good blend. I think of it as almost like a side gig, like a side hobby, where it's, hey, because I love teaching. I love talking about this stuff. And so it allows me to get immersed in the teaching side and out of the kind of office from the engineering, the hardcore engineering side. So I do the kind of the balance with both.
That's awesome. We were big fans of your flow chart on decision-making around heat pumps. Where in the country are you? Heating dominant, cooling dominant, and flowing down there. So we've really enjoyed a bunch of the stuff you've put out through the show. And through the show and a bunch of the sort of teaching stuff that you do, we get the sense that you're super into heat pumps. We get the sense that heat pumps have a special place in your heart, which is one of the reasons we invited you on. Why? It sounds like you have experience with all sorts of stuff. Am I right? And if so, why?
Yeah, you're definitely right. Who wouldn't love a heat pump? It's a magic box, typically, that sits outside, that heats your building, cools your building, may even provide some domestic hot water in the traditional sense. That is magic. I still am amazed how they extract heat when it's negative 13 degrees outside and how they cool when it's 120 degrees outside. It's an unbelievable piece of technology. I think that people underestimate, underutilize, and almost don't believe it. Yeah, so it's magic. Yeah, I love them.
Amen.
Us too. Yeah.
But I would also add that you got to properly apply it, properly design it, and there's pros and cons to all the different heat pumps that are out there, right? And so we don't want to say there's a one-size-fit type approach for heat pumps because there's air to air to water, water to air, water to water, right? There's all different versions of that. And you got to pick the right one and apply it appropriately and design it appropriately and get it controlled and installed. So there's a lot of stuff there.
So yeah, we definitely feel the magic part of heat pumps. But from your perspective, what do you think are the main benefits for a homeowner, for the occupants in the building, by going with a heat pump versus a conventional system?
Yeah. So right off the get-go, the heat pumps have this amazing efficiency to them, right? I think people are always amazed by, hey, I could put $1 of energy into this thing and I can get $3 worth or $4 worth of heat energy out. Like that, like, how does that work? How does that pencil? It doesn't make any sense whatsoever. And so like the refrigeration process and the heat pumps, that's the magic, is the efficiency, right? That is unbelievable. And there are very few mechanical systems that you can get more out than what you put into it. And so it almost feels like it defies the laws of physics. And so I think at the high level, okay, you have an amazingly efficient box that can heat and cool at these extreme conditions. And it's variable speed, right? So it can throttle up and down to meet these part load conditions much better than most of the traditional equipment can. It runs on electricity, so I don't need to have a propane or natural gas or oil, fossil fuel source for it. It's got all these different options for indoor equipment. Like I can go wall mounts, I can go ducted, and these are really quiet systems, right? And so you've got all of these advantages and all of these pros for heat pump technology compared to what's been available on the market for a long period of time. And so I think it's the next paradigm shift, right? But I also want to caution that the efficiency and cost are not always the same. So 3 times more efficient or 4 times more efficient is fabulous, But if you're paying 3 to 4 times more for electricity, it might be net a wash, or potentially we see this with natural gas systems. And so one of the kind of caution items I always say is that if you have a house that's maybe an older house that's naturally gas, it has natural gas and it's heated with that system, the horror stories that we hear sometimes that we don't want to hear is they ripped out the natural gas system, they went to heat pumps, and their electric bills went up. And they went up more than what the natural gas cost them that previous winter. And so we don't want them to hurt the homeowner's wallet, so to speak, by switching to heat pumps. When properly designed and applied, depending on where you are in the country, which has a big gap to it and wide width there, when you pull that all together, you try to figure out, okay, is the heat pump the right strategy for this house? And if you have propane, fossil fuel, oil boilers or something like that, oil furnaces, or electric resistance heat, it's pretty much going to be a win against any of those technologies to go to a heat pump. I almost don't even have to do the math out. It's almost always going to win in that situation. And plus, it's going to give you some air conditioning and dehumidification. So that's that. But with natural gas, you got to do your homework. And I mentioned this on the Ask This House, which system is right for you type of question. And that you got to do your homework when you compare it to natural gas in the traditional sense, depending where you are in the country.
Yeah, totally. It's definitely a danger to sell the technology, sell heat pumps based on financial savings only for those areas. Like you said, if you watch this ratio between dollars per therm and dollars per kilowatt hour, you certainly get parts of the country where your operating costs might go up. But there's all these other benefits of heat pumps, like generally comfort is much better, whether that's reduced sound like you're talking about, or you get, because of that variable capacity, you're able to match your load and to what you're delivering so perfectly that you get this incredible comfort, increased run times, better air filtration because the equipment's actually operating. But yeah, so it's all great points about heat pumps.
Yes, heat pumps win in almost every sense. When you compare it to natural gas, that's my only caveat is just compare that just to make sure that it's not hurting the wallet. That's the only caveat there. They're fabulous. And then now you take it one step further, you add solar to your roof. And people always ask me, all right, I'm building this new house, Ross. What system should I look at if I really want to future-proof my house and I want to look at it over the next 30 years, or I want to be able to give this to my kids someday? What should I be doing? Immediately, we're talking about solar panels with some electric heat pump of some kind, because now we can offset the solar production provides the offset energy that the heat pumps use. And now you can get to net zero, right? You can have that house produce as much energy as it uses over the course of a year. So we're designing houses that literally have no electric bill, no gas bill, no oil bill, no fossil fuel source whatsoever, no risk of backdrafting, no risk of carbon monoxide poisoning, yada, yada, all that, all the indoor air quality and other benefits that we haven't even talked about yet, but all of that. And they have literally amortized the cost of that over a 30-year or 25-year, rolled into the mortgage, and literally they have no extra bill for that. The only thing they may have is a water sewer bill, if they're connected to municipal water supply. That's it. And so that is where I think I would love to get to across the country. I know it's going to take some time to get there, but why wouldn't we be doing that? It's a perfect synergistic relationship to have solar with heat pumps, and then the rest is history.
Are you mostly doing new construction for residential or retrofits?
It's about 50-50.
Oh, okay.
50% of it's new construction. About 50% of it is renovation, typically major renovation, like gut renovations, typically. Sometimes deep energy retrofits. But yeah, about 50-50.
Great. So when you do new construction, you're starting with a blank sheet and you can do a bunch of this stuff. When you're doing a retrofit for a big old home but is less budget sensitive anyway, when you're doing one of those, the cost piece aside, what challenges do you encounter in a large home retrofit when thinking about putting in a heat pump system?
There's a lot. Anytime I deal with any old house, we just dealt with a project in Cambridge, Massachusetts. It was an 1840, I think, 1850 home. Very large. First thing was air leakage. The thing had 15 ACH 50. It was just leaky, right? Air sealing is not on the list of check boxes for an 1850s home. It's just not. And so it's poorly air sealed and not insulated, or really hardly insulated. So you got plaster and lath walls. You've got either stucco or brick siding. It's an older home and super leaky. And so the first thing is to make a building comfortable. The first thing I always think about is getting the building load reduced. What can I do to reduce the load of that building? Because if I reduce the load of the building, I permanently provide, regardless of what heating and cooling system I choose for that building, I've forever reduced the load and what that system needs to provide to that building. So we always look in our office, we always say, all right, we can produce more energy or we can consume less. And there's going to be a balance point depending on the project for those. And so we're trying to figure out where that kind of pencils out. And so in some cases, it would be so cost prohibitive to rip apart the entire building, to air seal it, insulate it, wrap it with exterior insulation, lose its character. A lot of these are in historic areas as well. So we can't even do that. That's not even on the discussion table whatsoever, because historic won't allow it, because it would lose its charm and its look, etc. But the first thing is, what can we do to air seal this building, and what can we do to reduce the heating and cooling loads by insulating and air sealing? So that's number one. Sometimes it's a gut renovation from the inside, and we have the ability to aero seal or do some sort of air sealing detail from the inside, and we can tackle some insulation from the inside. And so if it's a gut renovation, that's great, and we can go that path without affecting the exterior in a significant way. But then once you get past that, the next part is trying to figure out the heating and cooling strategies. And a lot of these buildings have 100 or 200 amp electrical services. And so they may have a natural gas or oil boiler that's providing the heating, and some of it's steam heat still. And so we're trying to find a way, like, all right, what's the best strategy here? So sometimes we are sizing the systems to provide air conditioning and supplemental heating, but the predominant primary mode of heating is still going to be that fossil fuel source. In some cases, it's some sort of hybrid heat pump technology where we're doing the heat pump itself, say, with a furnace or with a hot water coil coming off a boiler system. So we have the ability to go dual fuel that way. A lot of these projects, because of that update, they need a new electrical service, or they need some load management software, something that will have some hardware that has relays that will click on, click off effectively to make sure you don't exceed that 200 amp electrical service or 100 amp electrical service, depending on the size of the building and what they have. But we have clients that want to fully electrify, and it's a hard conversation to have with them to say, this building's going to be really challenging to electrify. And when we start to outline some of these costs to go to electrical service upgrades, induction cooktops, heat pump water heaters, heat pumps, and fully go down that path, it gets expensive.
Yep, for sure. So always great to improve the envelope beforehand, if you can, before you're thinking about the mechanical systems. Is there anything else when let's say you've got enough service, no issue around electrical service, and you're trying to go to 100% heat pump system? You're not going to use the existing steam or whatever system is there. What particular challenges do you have going that direction?
So you're saying remove the fossil fuel altogether? I mean, remove the natural gas?
Yes. Yeah. If that's the goal of your client.
Yep. And you're saying fully electrify that building, heating and cooling?
Yep.
And we have the ability to update the envelope, or no?
Either way.
So if you aren't going to be able to update the envelope, we're putting in now new ductwork throughout that entire building, more or less. That's going to be insulated, because a lot of times it's going to be traveling in a vented attic and potentially an unconditioned basement. And so we have challenges with duct leakage. We have challenges with duct sealing. We have challenges with duct insulation. So we got to get that solved. We are now putting in these systems with, obviously, it's going to be a lot of heat pumps, right? To be able to meet the load of that building, depending on the size of the building, we might need 5 heat pumps. We might have 5 air handler systems. And so it's going to be pretty disruptive to the building to get all that ductwork in, to get the air handlers in. We're going to have usually some sort of electric resistance backup, at least to deal with defrost cycling and deal with the kind of what if condition if the outdoor unit failed for whatever reason, or blocked with snow or something like that for the what if scenarios. But yeah, for poorly insulated envelope, it just magnifies. The ductwork gets bigger, the loads get bigger, the air handlers get bigger, the heat pumps get bigger. And I try to avoid that when we can, because we think that's not maybe the best approach to handling that building. I'd rather, for example, if I could handle the load of a building with a 2-ton unit for size and for the cooling demand with a 2-ton system, or if I have to fully electrify and go to a 5-ton system, which to do the heating and the cooling, because let's say the heating load is 5 tons, let's say the cooling load is 2 tons, I'm just making up some round numbers just for the sake of this argument. But the heat pump airflow goes up, the ductwork sizes go up, right? All of that goes up, everything spatial goes up, amperage goes up, everything goes up. So I would much prefer in that situation to go dual fuel, go with a 2-ton heat pump and put a hot water coil in off of that boiler plant and reduce this, get rid of the steam, get rid of the steam radiators, get rid of all that stuff, but be able to use that boiler system. Maybe it's a gas condensing boiler and running at 120-degree water temperature. So at least it condenses and has as high efficiency as it can. But at least that way, you get, to me, that would be a more strategic way of getting a heat pump into a building. The 2-ton unit can handle all of the cooling demands and can handle the marginal heating demands. And then we bring on that hot water coil in this example when we need to, when it gets cold out. So maybe when it gets to 40 degrees outside or 35 degrees outside, whatever that balance point comes out, we then kick on that system. But for all the hours between 35 and 95, the heat pump runs, it load matches, it's variable speed. And that also allows me to downsize my ductwork and my registers and my airflows. So I think that's a much more, in those older 1840s houses that have really poor envelopes, I think that's the best chance of success for most of those projects.
Yeah, it makes sense. And you get 80, 90% of the benefit by having that heat pump covering most of the hours of the year, both from a comfort standpoint, carbon reduction standpoint. And then you're not getting into all these like exponential increases in cost and complexity of having to redo the ductwork, having many multiple outdoor units potentially to try to serve that load. Makes sense.
Yeah. Yeah. And think about the electrical and say each heat pump runs, I don't know, let's make up a number, 40 amps, whatever the size of the heat pump is, depending on. So now if you have a 200 amp service and you got 5 of those heat pumps, guess what? 5 times 40 is 200. So you've got 200 amps eaten up in your 5-ton heat pumps in that example. You got nothing left over for anything else. And that's your heating system. And that doesn't account for anything else. If you have electric duct heaters or you have refrigerators, induction cooktop. So that's almost going to require an electric service upgrade at that point.
I'm so biting my tongue because you have almost exactly described my house, which is 1898 in Brookline. And I just want to extract free consulting from you, but I will not. I wish the folks who gut renoed this had talked to you before they did. We're not even going to publish this. This is just a ploy so I could ask you some questions about my house. As you were talking about this, I'm having 2 conflicting thoughts in my head. One is, oh my God, this is spectacular. And every home needs this. And I wish all HVAC installers could do it. And versus you are specifically focused on this segment of the market that can afford this sort of thing. What are the hours you're spending on a typical job to design? And I know you do all sorts of stuff, including fire and electrical, but if you just focused on the HVAC heat pump side, what does a design take you and your team in terms of hours?
Oh man, that's a loaded question. Yeah, a lot. Depends on, we're doing manual J, manual D, manual S. Is that kind of because that could be anywhere from a day to maybe a day and a half to do a proper manual J on a proper building, depending on what kind of information we have, is typically, it's going to take at least half a day. It's going to take 4 hours to do that if we have some piecemeal plans together. And we got to figure out the window heights. We got to figure out inputting. If you want to do a detailed load calc, to do it right, from my point of view, it's going to be half a day to do that. Plus, now you're getting into system selection with manual S and then duct design with manual D. RightSoft and other programs that we use make things move a lot faster than they used to. But we're still talking about a day to a day and a half for that level of work, depending on the size of the house. But if we're talking about the full CAD and Revit, we do stuff in Revit as well, which is 3D BIM. We're designing out every single duct in 3 dimensions on a building that's going to be coordinated with the structure and the architecture and other MEP items. So we do clash detection. We're talking about months, literally talking about months of design time. Sometimes we have a 6-month design schedule. Sometimes we have an 8-month design schedule. So I'd say minimum 2 months, maximum a year, depending on the size and scope of the project. So yeah, it's significant. But it requires that. If you want to do it right, you got to do the math, you got to do your homework, we got to dial it in. And we're talking about controls, sensor locations. How is the bath fan controlled? How is the ERV controlled? Where do those fan switches live? Where is my humidification sensor? Where's my dehumidification sensors? Where is obviously my air handlers, duct systems? Is there a steam shower that requires another additional exhaust system? Is there an AV rack that needs cooling, mechanical cooling to be provided? Oh, does that need mechanical cooling year round? All of those, there's a movie theater, there's some projector equipment. Okay, that requires some cooling. So there's these basically a domino effect. The building program dictates everything, and these programs get pretty sophisticated pretty fast. the control strategies, the number of systems, the complexity there ratchets up. And if we're doing everything in 3 dimensions, it takes time.
I think that's so helpful because like for who we're trying to reach with this podcast is heat pump entrepreneurs. And the vast majority of folks are not focused on the segment of the market you're focused on. But I think it's so interesting to hear how you handle that segment, because what does it look like if cost is not an issue? And so we paint this like holy land, right? What could be, and then the question is, all right, as you get more of a budget constraint, what do you have to do? But I think it's very helpful to hear your process and hear how detailed it is, but then also have these stats of budget's not an issue, 8,000 square feet on average. Yeah. So thank you for that answer. I think it's super useful for folks to hear, no matter who or what type of customer they're serving.
And I think you could still do a manual J, a manual S, and a manual D on any project of any size and any scale. And it doesn't need to be done by a mechanical engineer like us. An HVAC contractor, it should be well equipped to be able to provide that level of information and run those calculations. And so that's a thing that we teach and we talk about, and we want to make sure that every HVAC contractor can do that, because that's how you know that the system is sized and designed. And I think a lot of the skilled trades in the HVAC industry, they're so focused on the installation, the rebates, and moving on to the next project and the sales process. They're less focused on the design and application of the systems. And where I always say you could have the best installed system on the planet, but if it's designed wrong or applied wrong, you have zero chance of success on that project. And so you got to get the design and the application nailed down first, and then you have a fighting chance of getting the installation and success, basically a successful project at the end of the day.
That was awesome. You can't have a well-functioning system without both good install and good design. Like you absolutely need both. So 2 thumbs up on that one, Ross.
Yeah. Yeah, we got to hit that one over the head as many times as we can.
So I'd love to switch gears and dive a bit more into your experience, specifically with air to water heat pumps. Obviously, you're working in Massachusetts. You've got a lot of hydronic systems that are already in place. Air to water heat pumps are a great opportunity to be able to do some really interesting stuff in a house. And you mentioned with heat pumps in general, there's so much flexibility in terms of how you distribute and get that heating or cooling to a space. And with air to water, there's that many more options. Can you just talk a bit more about kind of your experience, and also just what are we talking about when we say an air to water heat pump?
Yeah. So out of all the heat pumps, that's my favorite. If I had to pick one, that if I was to pick a horse in the race to say 15 years, we have crystal ball 15 years from now, 20 years from now, what do I think the heat pump technology that will be the most adopted and respected heat pump? I think it will be air to water. I could be way wrong, but that's my kind of crystal ball. And the reason I love air to water, and the reason there's so many things. So where do I start? So with air to water, we're typically talking about a monoblock system, which means that the refrigerant is self-contained in the outdoor unit. So just like you would buy a refrigerator for your house that comes hermetically sealed with its own refrigeration process built in, I don't have to hook up gauges. I don't have to get into trim charge. I don't have to get into any of that stuff. Oh, did you triple evac? Did you braze with nitrogen? Did you get your flare torques done properly? All that goes away. All that goes away, right? So we have think of it like a refrigerator that you buy off the shelf, and now I can connect effectively water pipes. They are going to be antifreeze, propylene glycol water in a cold climate, of course, like here in Massachusetts. They can have a little bit of antifreeze in it with water, and that's what's going to come into the building. And that water is either warm water, let's say 120 to 140 degrees with current technology, or 45 degrees, 40 to 45 degrees if we want chill water. So I can either cool the building with the chill water, or I can heat the building with hot water. And so this is nothing new. Like this type of technology has been used commercially for people just call them chillers because they just produce chilled water. And those have been used for, I don't even know, maybe 100 years now at this point. So it's just like residential is usually the last frontier for HVAC technology to get to, but it's already been used. So it's nothing new there. The other thing too is that refrigerants are continuously changing and evolving. And so we used to be R22 Freon. Then that was mandated by the EPA to be not good for the environment, obviously because of the global warming potential. So they vetoed that. And then it went to R410A. So everybody went into 410A as the next refrigerant. That still has a GWP of 2000. That's still too high. So 410A is now being replaced with R32 and 454B. And so that's got a GWP around 500 to 675 in that range. So we're getting to better environmentally friendly refrigerants over time. But each refrigerant change and cycle comes with new challenges because sometimes we can't use the existing line sets between the indoor unit and outdoor unit. We can't, the new systems are not compatible with the old systems, right? If you change out your air handler, you have to change out the outdoor unit as well. And sometimes you need to flush and clean or even produce new line sets to connect the two. So the way I look at it is if I have water as my heat transfer medium in this building, I don't care about refrigerant changes in the future. I can take the box that's outside my house, I can rip it off the house and put a new box in, reconnect the water pipes, and off we go. So I can literally just continue to change boxes as I need to. The piping inside the building, guess what? It's plastic. It can be copper if you want it to be copper, but it's plastic. It's PEX or polypropylene. So all these issues with formicary corrosion go away. We don't have formicary corrosion with plastic piping. We don't have to worry about galvanic corrosion with plastic piping. PEX piping, polypropylene piping, that's the stuff they want to keep out of the landfills. The reason it's so good is because it's corrosion resistant to everything, just about. So now I have these pipes inside the building. So the arteries, so to speak, of the building are in place with a very high quality material from a heating and cooling perspective. And now, guess what? If I want to add a wing to my house, if I want to add an addition, I just can cut into that pipe. I can add some new PEX lines off of it, just like I'm adding a new fixture in a bathroom, right? We don't care about, oh, wait, I got to run a new line set. I got to get the trim charge right. I got to figure out a new outdoor unit that can do that. I don't care about that at that point because I can just expand and it's basically future-proofing built into that project. And so my concern is that we have these R22 systems that went in. And then when 410A came around, we had to rip out line sets in many cases to put in new line sets with new indoor units, new outdoor units to make them adapt to 410A. And I don't want to go through that with R32 and 454B. And then I don't want to do that again with the new refrigerants that come off after that, right? So we're at A2Ls right now. We're going to go to A3s. A3s are explosive. There are R290s like propane and CO2 and all these other things. So that's already been approved in Europe. It's already being used in Europe. So again, if I had the crystal ball, I think we're going to go there. It's just a matter of time. When an R290 CO2 or some other similar type of refrigerant is approved, we now need to figure out how to adapt that to the house. And I don't think most people want propane pipes running through their building for refrigerant systems. I don't think. And I don't think they're going to do it with CO2 that runs at 1,000 PSI pressure or higher. So I think if I can keep the refrigerant outside in a self-contained box, it alleviates a lot of those concerns. And so that's my rant on air-to-water heat pumps from just the technology and future-proofing. And the one thing I'll also add is that if you use an air-to-water technology appropriately with storage, you don't have to be affected by time of use rates. Because what I can effectively do is I can run my heat pump at night when electricity is cheap, store that energy in a storage tank in the basement or wherever in this house, and then I can use it during the day when power is much more expensive. So I don't have to run the compressor, I don't have to run the fans, I don't have to run that stuff. And so I can just pull off of that system. And then they have phase change material that can be used to make that BTU battery, the thermal battery, hold much more energy than just the volume of water that's in it. So like it again, future-proofs it and sets us up for a successful kind of rollout strategy. And I'm sick of having these trim charges be done, a flare nut be wrong, leak refrigerant, and then the system consumes more electricity than it was supposed to. Then it cuts out on pressure and just something that I've just seen too many times and I'd rather not do it.
I don't want to call it like a air to water maximalist or optimist. I definitely agree that there's some really exciting things to think about down the road as this technology progresses, that it makes sense as an end state technology for all the reasons you described. And then you didn't even get into the benefits of how you distribute. So you've got the hydronic system to get the thermal energy into the different spaces, but then you can use radiant baseboard. You can use radiant floor. You could put in a coil and for heating or for cooling in the space. It can be a high wall unit. It could be a floor unit. You have all of these options for how you actually deliver that thermal energy or extract it from the space. And so just incredible flexibility. Can you speak to one of the big challenges right now, which is for most of the products that are out there, they max out at a temperature of around 140 degrees Fahrenheit. Are you seeing products starting to come into the market where we can get to higher temps, like a typical, like my house here in Maine, The hydronic system was designed for the emitters to be running at 180 degrees Fahrenheit.
Yeah, design day. Yep.
Yeah. Yep. What's the latest on getting that higher temp air to water system?
Yeah, so the 410A air to water units top out at about 125, 130 degrees, give or take. Unless you have EVI technology, which is enhanced vapor injection, then you can get up to about 140. The R32 and 454B units are going to 140 degrees, and some of them actually push that a little bit higher, can get into 145, 147, even topping out close to 150. So the new refrigerants definitely give us a little bit of boost there and better efficiencies. The CO2 versions and the R290 versions are going to be running up to about 170 Fahrenheit, some of them even 180 degrees Fahrenheit. So each kind of phase and version of the refrigerants and the new versions of technology continue to push those temperatures higher and higher. So if you get enhanced vapor injection with one of those refrigerants, yeah, we could get to a point where we could replace your boiler system effectively with let's say a CO2 or R290 air to water heat pump connected to those radiators, and you can get to 180 degrees on design day. We can do that. So yeah, a lot of that stuff's available in Europe. We have some other issues here, like EPA has some limitations on the amount of R290 as an example. There's a volume limit inside the heat pump. So we need that to be relaxed. We also need ASHRAE to get their regulations and standards and safety thresholds up to current standards. On that front, we need obviously the trainings for the installers and the tools to make sure that they know how to service and properly handle these refrigerants as well. So there's a road there, but I'm hoping that's going to come faster than expected. But yeah, it's going to be at least a decade to get there.
So are you using air to water systems today? Or no, you're just excited about them? You are.
We start with air, almost on every project, we start with air to water. Let me start by saying new construction, we start with air to water in our discussion. Air to water is our starting point, and we usually provide like a good, better, best strategy, and we talk about the pros and cons. We have a whole presentation we give to clients is which system is right for you. And we talk about air to water, we talk about geothermal or ground source heat pumps. I call it geothermal because everyone refers to it as geothermal, but yeah, ground source heat pumps. We talk about traditional mini splits and VRF technology, and we talk about your traditional kind of hybrid system, furnace, heat pump, or hot water coil heat pump. So those are the 5 systems that we basically explain pros and cons to, but we start with air to water. That's the one we start with. Unfortunately, we probably have 50, maybe north of 50 in terms of air to water projects that have been running. And so hydronics was what I was taught early on. So I'm definitely a hydronics guy. John Siegenthaler is one of my mentors. Learned a lot from him, learned a lot from Robert Bean, my father, just a bunch of people in the industry that are all hydronic heads. And we all kind of stick together, but we're trying to get the information out there. This stuff is not rocket science. We can do it. And so, yeah, air to water is here to stay, and we're doing it.
Do you ever use it in retrofit situations?
We do. Yeah. So like some of those older houses, like we talked about in Boston, let's say, or in Brookline, where let's say they have radiators, and let's say they have oil boiler or a gas boiler that's providing the heat through a forced hot water system in that house. What we'll do is we can do air to water running in parallel with the boiler system. So we have basically an outdoor reset curve that's established. And so the air to water basically runs to heat that building when it's more milder out, and then the boiler kicks on when it gets colder out. And we basically adjust that reset curve so we can shift between the air to water heat pump and the boiler. And so we're doing that today. Yep.
Nice.
Yep. And then new construction, we do it a lot too. And then we pair it up sometimes with radiant floor heating, like Eric was saying. And we'll pair it up with trench heaters, that these flush mounted elements that sit into the floor. So they're super aesthetically pleasing and provide that kind of gentle heat over a wall of glass. We've done the air to water with hot water buffer tanks, with chill water buffer tanks. So we can even do simultaneous heating and cooling. We do it for domestic preheat in many cases because we're going to store that water in a buffer tank. Why not let it do our domestic hot water and our space heating? So I didn't even mention that. The air to water can give us domestic hot water as well, which VRF units and mini splits can't. The other thing too that I think is better for the southern markets, which we don't get involved with as much, but I just want to mention is that when you have hot water and chilled water, let's say at 45 degrees and 120 degrees, I don't have a risk of freezing up an evaporator coil. My indoor air handler coil I don't have to worry about I need 350 CFM a ton or 400 CFM a ton, otherwise I'm going to ice up. And no, that all again goes out the window. I could run a system on 200 CFM a ton, 150 CFM a ton. So now when you get these micro loads in a house, let's say you have a new construction home with a bedroom that has a 500 BTU load on design day or a 1,000 BTU design load on design day. Find me a heat pump that can deliver 500 BTUs on design day or 1,000 BTUs on design day. You can't, but we can put in a hydronic system that can absolutely deliver 500 BTUs because I can throttle the flow rate down. I can throttle the temperature down. I've got more levers to play with on that one. And so then you can go in the southern market where not only do I have a small cooling load, but let's say I have a big moisture load. Let's say my latent load is really high. I can put 40 degrees into that chill water coil and I can turn my air handler all the way down to its lowest speed. And my sensible heat ratio can go from 0.9 down to 0.4. And now I'm just letting all that dehumidification happen. All that moisture is dripping off that coil. The coil is saturated, soaking wet, draining away. And I'm having very little change in the temperature of the room, but all the moisture is being wrung out off that coil. So now I can do dehumidification. I can do reheat. I can do heating, cooling. I can add humidity. God, this stuff is awesome.
Totally. And then and I know there are systems folks are working on to do heat recovery as well. So if it's in the summer season, you got air conditioning loads, instead of just dumping all of that energy outside, you can put that into your buffer tank. You can use that for domestic hot water. And so you've got so many knobs and levers that you can pull to just truly optimize this system. And we know that homes are a system, and we want to be thinking about the comfort issues in the home. Maybe we're thinking about our electricity consumption and grid issues. With all of these different knobs and levers that we can pull, we can optimize all of these different aspects and really have an amazing outcome.
Absolutely. Yeah. Heat recovery chillers or heat recovery air-to-water heat pumps are available commercially. I haven't seen a unit that does that residentially yet. Most of the stuff is going to be three-phase, larger tonnages, but I think that will happen. And so you're right. It's like a water-to-water heat pump that basically can move heat from that where we need cooling and push it into the hot water side or the heating side. And so when you have these larger houses that have simultaneous heating and cooling loads, let's say you have AV racks running that need cooling, an elevated machine room that needs cooling, and then you need domestic hot water and space heating in the north side of the house, I can literally move heat effectively from the elevated machine room and the AV racks or the mechanical room that's overheating. I can run that heat, pull it out, strip it out, and dump it into the hot water side and send that to the north side of the building or to heat my domestic hot water. And now my COPs go up to 7 if I'm doing heat recovery. So I'm no longer in that 3 to 4 limitation. I'm now in the COPs of 6, 7, 7.5, that range. And so that's fabulous. No more defrost, right? The air-to-water heat pump goes into defrost. Who cares, right? I've got all that volume of water. I've got the buffer tank. It's almost got those protections built in. So yeah, there's a lot of reasons to love it.
Ross, we've had a few conversations with folks who the air-to-water heat pumps in the US sound like the end of the rainbow. It's there, but you can never quite get there. It's always just a little bit ahead of you. So to hear you've got a bunch out there using both in new construction and retrofits, if someone out there if there's a HVAC entrepreneur out there who's curious about getting into air-to-water heat pumps sooner rather than later, and they're operating in a space where budgets are constrained, how would they do it? What advice would you have for them?
First thing starts with training, right? And so any of the manufacturers that sell air-to-water technology in the United States, most of them that I've seen have a robust training platform. So a lot of those, they have on-site locations with working equipment that people can go touch, feel, see, get acquainted with. And then they have those design and application sessions and trainings to complement that. I would say for any HVAC contractor, reach out to one of the local air-to-water manufacturers and partner up with them. They also are going to get inbound leads to them from homeowners that hear these podcasts and other things. And they're going to say, hey, I heard about this air-to-water stuff. It's really cool. Can I get a quote on it? Can you install it? And so it's a way to differentiate yourself if you're an HVAC contractor. And I think all roads lead to this type of technology. So it is a little bit at the end of the rainbow, but it is obtainable. It is here to stay. And there are definitely a bunch of resources now. There's also different webinars. There's a bunch of YouTube areas and locations that have a tremendous amount of information. I should say YouTube channels that have a tremendous amount of information. John Siegenthaler does a lot of training on this. We talk about it in our Building Science Symposium group that travels around the country doing different 2-day stuff. We're going to be at Kansas City, Cincinnati, and Philadelphia the rest of this year. Yeah, there's a bunch of outlets for people, more than ever before. So I think it's a great thing that most HVAC contractors should consider. Now, I would also want to mention some of the cons, right? There's an upfront cost difference, right? So the technology is very new to the US. So that comes with, they don't have the economies of scale yet. So there's a upfront cost difference and delta there. And especially if a contractor that's never done it before, he's going to pad his number to make sure that he's covered. So that's another thing to be aware of if he's never done it, because he's venturing into uncharted territory, so to speak. So there's that. There's also, because we're talking about chilled water, there's always a risk of condensation and sweating on that pipe. So we got to make sure that the piping and the valves, et cetera, and pumps are properly insulated continuously and sealed. So we call it vapor sealed and insulated across its entire length inside the building, because we don't want to have dripping pipe in an attic sweating, so to speak. We do have antifreeze in the building. So it's going to be a mixture typically of water and propylene glycol. Propylene glycol is in salad dressing, so it's usually not a huge ordeal, but I just want to make sure that people know that it's not pure water in these systems in a cold climate. There's going to be some mixture, maybe 20%, 30% propylene glycol, 70, 80% water mixed together. And that glycol does break down over time. So usually every 5 years or so, we need to do a pH test just to make sure that it hasn't turned into glycolic acid. And so that's just one of the maintenance items that needs to be checked. But the rest of it inside the building is no different than any other kind of hydronic and air handler system. It's ductwork with filters that need to be changed and stuff like that. But I just want to make sure that we mention some of the potential cons that may come up.
Just briefly, I wanted to circle back to something you touched on at the very beginning, your interest in solar in particular, and this beautiful match of having rooftop solar, on-site solar, and a heat pump system. Can you just talk about your approach for doing integrated design between those two systems and how you handle that at your firm?
So we'll always have a load calculation on the building. So we'll have a main OJ done. So we'll know the heating and cooling loads of the building. And what we'll do is we'll actually simulate that on a building with a certain air to water heat pump or whatever technology we have to see what the energy use in kilowatt hours are for heating and cooling over the course of a year. So now we know how much energy we need to heat this building. We know how much electrical energy we need to cool this building. So we have that as a starting point. And then we say, hey, Mr. Homeowner, we've modeled it. We expect the building to consume this much for heating, this much for cooling. Would you like us to consider, or would you consider doing solar to offset the heating and cooling energy of that building and what that would look like? And most homeowners would say, yes, that would be tremendous. Let's take a look at that. Some homeowners say, no, I don't like the aesthetics and I've heard it doesn't work and yada, yada, yada. So there are some negatives or naysayers out there. But in general, most homeowners and architects are open to it. And then we usually do a couple of different system iterations. The first iteration is offsetting 100% of the heating and cooling energy for that building. We look at a second iteration depending on roof orientation, shading, and what the site can accommodate to see whether we can get to that building to be 75% or 100%, meaning offset. We take into account plug loads, so refrigerators and all that kind of stuff rolled into the model and simulated. Lighting is rolled into the model. Domestic hot water is rolled into the, so we can get to a point where we could size the solar for 100% of what the expected energy use of that building is going to be. And so depending on what the homeowner, wants and what the budget is and what the roof can accommodate, that's usually some sort of solar usually lands on that project. Sometimes we get into the discussion about backup power. So sometimes that leads us to a battery solution with a lithium ferrophosphate type of battery solution to offset the critical loads of the building. Sometimes it is a generator, backup generator solution, and sometimes it's both. It's a battery solution with a backup generator, depending on if we have a homeowner that has the Armageddon scenario where they want to be fully covered. So it really depends, but that's usually the kind of the outline of where the kind of the system design process, how it unfolds on the electrical side of things.
Makes sense. So just like any other system, it starts off with good design, manual J, S, and D, get the loads figured out, get the right equipment, and then you can size the solar system depending on the homeowner's goals or what the performance of the equipment is.
That's right. In some cases, we've also had ground mounted solar where we couldn't do it on the roof of the building because of tree lines, shading, or for visual aesthetic reasons or whatever it may be, or historic. Because the south side was the front facing part of the building. So historic wouldn't even allow us to do it. So when we get into those situations, sometimes we do ground mount. So if they have the landscape and let's say in the backyard to do it, that's sometimes what we do. So it's not what I start with, but it is another option. And then whether it's batteries or set up for future batteries, that's another one that we go to. So the infrastructure is in and ready to be accommodated with a battery solution, but the batteries aren't installed now. They're added at a later point in time. And yeah, so that to me is a nice way to do it, depending on budgets and goals and expectations.
Ross, this has been awesome. We'll get into our sort of final area of questioning. So in your role, it's a really interesting segment of the market to play in. So I imagine you just see spectacular contractors. So in your experience, what separates like the top 5% of HVAC installer from the rest of the playing field?
So you're right that the projects that we get involved with are obviously very complicated, very high stakes type projects. And so usually we are dealing with what I consider to be an A-level contractor, both from the general contractor all the way down through HVAC, electrical, plumbing, and everybody on that project. And so everybody has a similar interests to get the job done and get it done well. And I think there's also help knowing that there's an engineer on the project that's basically quarterbacking, so to speak, the project. And the way that we always come to market is, look, here's our design. Here's the goals and expectations that we have. But if you see anything that you think we should change, modify, that you're concerned with, let's talk about it. And usually we have a meeting on site to say, have you reviewed the drawings? Have you reviewed the building? What challenges, what questions do you have? And sometimes an HVAC contractor, electrical plumbing contractor, they bring some really good suggestions, and we'll actually modify the design so that we're all bought in to making sure that we have a successful outcome at the end of the day. In some cases, we get involved in a project and there's a suggestion that's made, and that's because they don't know what the goals and expectations were for the get-go for that project. So it's just a drop in information. It's just that the communication path was dropped. And so once we explain it to them, we designed it this way because of whatever that may be, then they go, oh, now I get why you're making us do it that much more challenging way. And it's not because we want it to be more challenging. It's because there's a reason that was selected or that was chosen, whatever system, whatever the constraint or concern was. So we're always trying to figure out how to get the right players on the team and how we all can work together to make sure we have that successful outcome. And I know that's not the norm in the industry, but I do think that's a big part of why the projects that we've been a part of have been successful and why we've grown over the last 15 years of doing this is because of that. People know they trust us. We have a long-term view, and the way we look at the house is, hey, if this were our own house with this style of budget, what would we want? And if you apply that type of filter, you're going to have a much more successful outcome at the end of the day, especially if you have the goals and expectations from that homeowner from the get-go. So the contractors that we do work with, they are the A-level contractors, and they are, I think, the best in the industry because they have also that long-term view for their business and for what they want. So if most of these companies are family run, they're not private equity owned. They're family run businesses that usually are multi-generational. Some of them are the grandfather started it or the father started it and the son's not running it, et cetera. They have a vested interest to make sure that business succeeds. So they're not going to cut corners. They want to do it right. And so they also, most of these companies reinvest into their company in terms of they provide their contractors and their employees with proper tools. They provide them with proper training. We get the out of office message from a contractor saying, our staff is at training for the next 2 days. Unfortunately, if you have an emergency issue, call this person, right? There's one person manning the ship back at the office, but everyone else is at training, learning about air to water heat pump technology, right? And so they provide 401ks for their employees. So there's a completely different viewpoint for a family-run HVAC business that has a long-term view versus a sales-driven organization that has a short-term view that's potentially owned by some conglomerate 3,000 miles away. They're coming at it from completely different angles. And that's why we like to work with those type of A-level players. And that's why they rise to the top in the marketplace.
I love that answer. And Eric and I are biased in that direction too for how we run Amply. We just raised from sort of friends and family and grants and yeah, that's the kind of business we want to build personally. So fascinating to hear that you see that as a differentiator for who you work with as well. Although not surprised, fifth generation plumber, your dad runs the business. That makes sense, but nice to hear anyway.
Yeah, there's almost a sense of pride there, right? For that like next generation taking over the business. Like, hey, I don't want to let my grandfather down. I don't want to let my father down. I want to make sure this thing continues to succeed. In most cases, we find that type of business, especially what's that stat about most businesses fail after or don't even make it through to the next generation, isn't it? I remember there's a crazy stat about how many businesses actually succeed to the next gen.
Yeah, most businesses don't last past 2 years, let alone to the next generation. And actually, we get hit up all the time. Most podcasts don't make it past episode 8. So I think like a lot of things just get left by the wayside. But yeah.
Yeah. So if you've got a business that's lasted through a generation and is potentially in the second generation or even third generation, you know that there's a good system there. They've got some good ethics. They've got some good trainings. They've got some good pride in their business and what they do. And those are the companies we like to work with. And I will say that most of those companies that are aging, that have aging owners that might not have, let's say, kids that are taken over, don't have maybe a proper succession plan, a lot of them are getting inbound requests from private equity, conglomerates, and other types of businesses that want to purchase their business. And so there's a lot of consolidation happening that I'm seeing across the country in the mechanical, electrical, plumbing, contracting, and vendor industries.
For sure. Yeah. Ross, this has been so fun. I would love to wrap things up with one more question. Any other specific resources, trainings, books that you'd recommend for HVAC contractors that are out there trying to do this stuff the right way, trying to level up?
There's a bunch of resources. I think of the HVAC school. Brian Orr is doing a tremendous job down there. Has some great content. The AC Service Tech, Craig's doing a great job with that. Obviously, YouTube is a tremendous resource. You just got to make sure you're in the right channel, but you can go down the YouTube rabbit hole and you can get some unbelievable information nowadays that it's right at your fingertips there. It's like so that, I can't count that out at all. There's obviously the traditional textbooks and stuff like that. Residential Energy by John Krieger. There's Modern Hydronics by John Siegenthaler. There's a bunch of those books that are sitting on a bookshelf right over there that have a tremendous amount of information in them. I know that most people aren't going to spend hundreds of dollars on these textbooks. And there's that. There's BPI certification. There's NATE certification. There is obviously the manufacturer trainings, as I mentioned previously. There's a lot of information that's out there. You just have to, one, be curious, and you have to have the initiative to go get it.
Some answer. Ross, thank you so much for joining the Heat Pump Podcast.
Thanks for having me. This was awesome, guys.
That was fun, Ross. Thank you. Thanks for listening to the Heat Pump Podcast. It is a production of Amply Energy. And just a reminder that the opinions voiced were those of our guests or us, depending on who was talking. If you like what you've heard and haven't subscribed, please subscribe in your favorite podcast platform. We'd love to hear from you, so feel free to reach out. You can reach us once again at hello@amply.energy, no.com, just .energy. Thanks a lot.